Greetings from Medines Technical University, Ankara, Turkey. I am back, the team lead of the METU ROVER team. Today, I will present you this year's rover, which is Rigel. Our team consists of 29 undergraduate students who are working under the 5 sub-teams. Mechanics sub-team is responsible for mechanical design and manufacturing. Electronics sub-team is responsible for designing electronic components, power, and communication systems. Software sub-team is responsible for autonomous driving and computer vision algorithms. Science sub-team is responsible for scientific exploration and assessment of the Mars yard. Organization and finance sub-team is responsible for documentation, presentation, and finding financial resources for the team. Being a part of OnSite Challenge offers a unique opportunity to compete in on-field robotic solutions can be implemented together. Moreover, this competition lets our team to be a part of community, both collaborating and competing. This nurtures our creativity, as well as giving us a preview of international scientific efforts.
As the mechanics team, we are responsible for designing chassis, wheels, robotic arm, science systems, and integration of the other mechanical components.
The chassis of rover is designed using aluminum sigma profiles with appropriate corner fasteners to ensure reliability and ease of assembly. A rocker suspension system was designed and implemented on the vehicle to keep the chassis parallel to the ground while the rover in motion to protect electronic components. The suspension system enabled the vehicle to move smooth over rough terrains thanks to the differential bar that acts like one-to-one gear. The locomotion motors are housed within aluminum enclosures to prevent collisions with the terrain, and double bearing supports eliminate reaction force on the motors. The torque is transmitted through the rims and designed body on tires. Various analyses were conducted for the tires, and TPU 3D printing will be preferred. The robotic arm, measuring approximately 1.2 meters in length and 9 kilograms in weight, is designed to perform manipulation tests required for the competition. Aluminium 775 was chosen as a structural material for the 6th degree of freedom robotic arm, while 3D printed PDR Plus was used for the gripper and connecting parts. Various methods for the torque increase and transmission across different axes were employed, such as step motor, belt drive systems, and linear actuators. In the gripper design, rectilinear motion was preferred, and 4-bar parallelogram mechanism was used to achieve this motion. In that subsystem, the torque is provided by a servo motor.
As an electronical team, we are responsible for the rover's power management, motion control, sensors, actuators, and both onboard and off-board communication. Our goal is to provide reliable, effective electronical solution in the most convenient way. To start with the rover's power system, a custom-designed battery was built to power more than 20 motors and all-electric equipment, including antennas and computers. Consisting of 3 cells and a total of 18 high-performance lithium-ion batteries, each battery can provide up to 100 amps of current. Joints of the robotic arm will be teleoperated to a desired configuration using manual joystick control. Movement motion planning library will be used to solve for inverse kinematics and plan a collision-free path through the environment. Wireless communication will be facilitated over 2.4 GHz Wi-Fi network with the Ubiquiti Bullet M2 booster for better long-distance performance. Custom communication protocol has also been designed to reduce data transfer between the rover subsystems and the ground station. To keep system complexity at a minimum, multiple relative components are collected into the same circuits being designed for each system. A custom motor control unit capable of controlling both position and velocity has been designed. An e-setup button is placed on the chassis to be able to quickly respond in a case of emergency.
As a software team, we are developing all the peripherals of the rover, such as algorithms, drivers, and sensors, by utilizing advanced simulation programs and other programming tools.
A custom signal processing algorithm was made using computer vision libraries in order to detect location and orientation of the probe. According to the specifications published in the manual, a replica of the panel was made and used for the training of the machine learning model. We developed an algorithm to detect the posts and gates and published the relative location of each leg to go through the gate, which is essential to complete the autonomous navigation task. A ROS-based navigation stack called MoveBase is used for the locomotion of the rover. A state machine leads the rover to start any navigation legs, inform the operator after AR tag detection, and traverse back to the initial point once all the legs have been reached. Camera is placed on the front side of the rover, and it supplies a stereo video stream. Moreover, Z2 wrapper library publishes the stream as a ROS message for the use of the localization, navigation, detection, and mapping applications. A custom GUI was made using Python in order to visualize and examine the data coming from various sensor sets, such as science and GPS.
The science team utilizes an interdisciplinary approach to conduct comprehensive research on the geological diversity and astrobiological potential of the Martian. The assessment starts with the sampling process facilitated by the integrated driller mounted on the rover. Driller enables the acquisition of samples at a depth of at least 5 centimeters without mixing the sediments. Subsequently, the collected samples are transferred to a storage module, which can move in a line and rotate. Meanwhile, each sample container is meticulously designed to seal the sample from the external environment. Integrated sensors within the storage tubes measure the sample's temperature and relative humidity. Furthermore, onboard cameras are employed to identify the mineral composition of rocks through the utilization of CNN image classification algorithm developed by the team members. The presence of complex organics such as peptides and polysaccharides are important signs of biological activity. To receive accurate readings for the presence of such components, colorimetric assays such as bioret reagent and Lugol's iodine are preferred. JMARS is utilized to conduct a geological assessment of the given Mars yard since its layers and databases provide significant insight into Mars regions.
A FPV drone will be placed on the rover for the navigation test. Our drone has 4 motors that are capable of reaching a long range of speeds. Onboard camera allows the team to take photo. Also, the drone will be positioned on the rover with an arco marker special for the drone. Location of the drone will be tracked and published to the GUI. With the help of FPV drone, we are aiming to reach recent trends in the robotics field, especially specialized for the space exploration.